This week we are going to talk about thermodynamics, but we're going to take an introductory look and we're only going to look at enthalpy, a little bit of Hess's law, and in Hess's law we'll be talking about two different kinds of problems, and then some thermochemistry, basically like if you heat up some water, how much energy does it take to raise the water 1 degree Celsius, that kind of thing. When we take a look at this again, we'll be talking about entropy and some free energy, but that's for a later date. This is just going to be a simple introductory video to begin with. Thermodynamics is really the study of energy and its interconversions. Now, we can store energy in lots of different ways. The first one we're going to talk about is chemical potential energy. So that is literally the arrangement, how the atoms are arranged. So if I were to pack in some atoms here, nice and tightly together, that actually has a low energy. There's not much going on as far as like energy change that can occur there. Whereas atoms that are further spaced out, like if we had kind of a gas arrangement, something like that, there's actually a lot of energy that could be released from that system when the atoms all approach each other. You can think about it in terms of like when gas particles form a liquid, that process of condensing down into a liquid can release a lot of energy. So there's storage in there. Some people will say like chemical potential energy is the energy stored in the bonds. That is a horrible, horrible thing to say, especially to an AP chemistry student. Energy is not stored in bonds. In fact, we will talk over and over again about the fact that when you create a chemical bond, you're actually releasing energy. So if you see this definition, I need you to ignore it. Chemical potential energy is not the energy stored in bonds. It's just energy that is due to the way things are arranged. Kinetic energy is another way that atoms can store energy. They store it in their motion. So if we looked at that, let's say we have some particles here that are flying around. They're moving super fast in all directions randomly. And then over here, let's say we have another set of some atoms that are hardly doing anything, right? They're just sitting around. When this atom comes in screaming fast and hits the other one, we could get like a collision that occurs, and then it's going to transfer some of the energy from this particle here to that particle there. And so the first particle will bounce off, losing a little bit of speed, and this particle here is going to gain a little bit of speed. So that transfer of kinetic energy is another way that systems of particles can move energy from one particle to another. Lastly, there's a term called internal energy. We don't deal with that much, but it is the sum of potential and kinetic energies of a system. So if you add the potential and the kinetic together, you get the internal energy. Which leads us to the next question, which is, what is a system? Well, a system is anything that you choose. It's usually a set of objects that you are interested in. In chemistry, generally, it's pretty easy to choose a system. Let's say you have a beaker with some chemicals in it. So here's my beaker with some chemicals in it. I would say that the chemicals right in here are your system. And then everything outside of those chemicals are called the surroundings. So anything that we're interested in is the system, and the surroundings are everything out there. Now, how does energy get from one place to another? I kind of described one method when I was talking about the kinetic energy. But let's start off with this term called working. Working is when chemicals do physical work on their surroundings. So let's say I have a reaction that produces a gas. that gas doesn't just sit in there, right? It's got to form. Let's say I mix baking soda and vinegar together, and they form bubbles. Now the bubbles form inside the liquid. So as that bubble forms, it's got to push the liquid out of the way so that the bubble can become like hold the gas in there. And that process of pushing the gas out of the way is called working. It is like physical pushing of chemicals against their surroundings. Another way that chemicals can like throw energy around is called heating. And that's where the kinetic energy of two particles is exchanged during a collision. So let's say you're running down the hall, you're running top speed because you're late for class, and you run into a freshman. You lose some of your speed, but you push the freshman, and now the freshman has more kinetic energy. So you're transferring energy from one particle to another. Okay, now the process of pushing energy into a system or out of the system is given names. So when energy leaves a system, so if I have the energy and I'm pushing it out, that is called exothermic. Now, why am I calling myself the system? Because I'm interested in me. Okay, so I called myself the system. Could I make something else the system? Sure. Like, you get to choose what the system is. But usually, as we said before, in chemistry, it's like a beaker. So if I've got a beaker, and beaker is like radiating heat outward, we call that exothermic. Now, that's weird. If the beaker is throwing heat out, isn't the beaker itself, like the inside, getting colder? And the answer is kind of yes. But I would look at it a different way. The chemicals are really what our system is. And the chemicals have this either potential or kinetic energy that they're getting rid of. They're trying to get rid of it. And they're doing that by pushing the energy out of the system. And so the system is losing energy, and the surroundings, the water and the beaker, are gaining it. And so you feel the beaker get hotter because the chemicals are pushing this energy into there and literally pushing the energy into you. Okay, so that the energy that was in the chemicals has come out and is going into your hand, and your brain says, whoa, that's hot stuff right there. That is warm. If we go the other way, we call that endothermic. Anytime energy goes into a system, that's endothermic, or endothermic. Now, generally, if you were holding a beaker and there was an endothermic reaction going on in there, the beaker is going to feel cold. Now, so there's chemicals in this beaker, right? Chemicals in, let's see if my pen will work here. Here's my beaker. Boom, here's my stuff. And the chemicals inside here, which I'm just going to represent with it by a rectangle, are trying to absorb energy. So they need energy to come from outside the system and enter right there. And where's that energy going to come from? It's going to come from you. You are holding the beaker. Your hands are at 98.6 degrees Celsius. You have a lot of heat energy inside you. And what's happening is the system saying, ooh, I can't wait to get my hands on that. Quite literally, like it's sucking out the energy from your hand and putting it into the system. Okay, we need to talk briefly about a state function. Now, a state function is any kind of change in which the actual path from one place to another does not matter. So for those of you who have taken a physics class, let's say I need to get from point A to point B. I could go straight there, point A to point B. Or I could take this path back and forth, right, to get to point B here. Oops, my pen, there we go. I get to point B. Oops, my laggy pen's weird. Okay, now, in a physics class, we could say that both of these people went the same displacement. They went from A to B. right? But they did not cover the same distance. Oh, the first person went direct. They had a short distance. The second person went back and forth, back and forth, back and forth. That's a huge distance. So if you're in a physics class, we would say that displacement is a state function because it only depends on where you ended and where you began. Okay, and we're always going to take where we end and subtract where we began. Why is that important in chemistry? Well, think about it. 100 years ago, chemists really had no idea what was going on inside a beaker. You might throw some chemicals in, and so you knew what you put in the beginning. But then the next time you could pick it up was, what did I make? It was tough to figure out, like, what is actually happening on the inside. And there was a guy named Hess who figured out, doesn't matter. The only important thing is, what did we start with and what did we end with? And as long as I can make any plausible path from beginning chemicals to ending chemicals, that will be sufficient. And if I choose a different pathway from one set of chemicals to another set of chemicals, and you choose a different pathway, even though we solve radically different problems, we will get the same answer, because all that matters in this thermodynamic problem is, did we start in the same place and end in the same place? Okay. So what does heat change look like on paper? You're going to see these graphed a lot. And so I'm going to start here on the left, and I'm going to say, like, what kind of heat change does this show? So it's usually easier if I put in some numbers. Let's say I call this 10 joules of energy down here. And up here, I say that this is 100 joules of energy. And I'm totally making this up. Doesn't matter. You could put any numbers in there. But how do I get these chemicals, this ammonium nitrate, to go from having an energy of 10 joules to ammonium nitrate that has an energy of 100 joules? And the answer is, I have to insert energy. I have to take 90 joules of energy somehow and push that into the system. So that's an endothermic reaction. My chemicals in the beginning have less energy than they do in the end because I've pushed energy into them. How about this graph right here? What kind of graph is this? Is it endothermic, exothermic? Well, again, we have nice numbers. We've written in our reactants start at 100 joules. And apparently we go up to 400 joules, and then it looks like it settles down around 300 joules. So how did I get from 100 to 300? Well, I had to push energy in. I had to insert 200 joules of energy here in order to lift my beginning chemicals from 100 up to 300. We should also talk about this energy right here. It's the energy between where we finally ended up and like this peak. And that's called my activation energy. Oh, I said that wrong. Sorry. I have to correct that in post-editing. My activation energy is actually right here in A. That I have to lift it all the way up from 100 to 400. That's called my activation energy there, which is why this thing is called an activated complex. So the activated complex is a chemical that might only last for like a split second. It's something that is not very stable, but that forms needing a lot of energy. And then it says, like, well, let me get rid of some of this energy and actually become a stable chemical, which we're going to call our product. We'll talk about that a lot more in the days to come. Okay, the last graph that you may see, I tend to call these like Hess's law graphs. I don't know if that's their official name or not, but they are a little weirder. You could generally start anywhere you want on these graphs, but since this is an intro, I'm going to start in the simplest possible space, and I'm going to say that these right here are my reactants. Right there. So I've got some methane and some oxygen, and I'm going to burn them. I'm going to add them together. Now, I could go in one step. Methane plus oxygen gas goes to carbon dioxide and liquid water. Boom, do that one step. And apparently, according to this graph, I would get out 890 kilojoules. Now, so first of all, kilojoule is 1,000 joules. So, and I know that I get it out because it's negative right there. That is a negative number, so it's coming out of the system. But that's not the only way this could happen. Maybe I take my methane and my oxygen gas and I burn it and I get carbon dioxide gas and water vapor. So wait a second, why would that happen? Well, I just burned something, it's pretty hot, right? So the water probably isn't going to form a liquid right away. So maybe it stops along the way as carbon dioxide and water vapor and it sits there. So I get 802 kilojoules out the first step, and then some time goes by and the water condenses into a liquid. So it goes from being vapor to a liquid, and that process gives me an additional 88 kilojoules out. So if you said we went in one step, you would say, well, that's 890 kilojoules. I would have said, well, maybe it takes two steps, but if you look, if I add up my two steps, we get to the same total energy, which is what Hess is going to say in Hess's law. Last thing for this video, we're going to talk about the first law of thermodynamics. So believe it or not, there is a zeroth law, and the zeroth law says that if I have three objects, object A, object B, and object C, if object A and object B are in equilibrium, meaning essentially they're at the same temperature, right? So if A is a little bit hotter than B, then A will kick heat over. And if B is a little bit hotter than A, it will kick heat back to A. But if they're in equilibrium with each other, then they're just equally sharing the energy. And the zeroth law says that if A is in equilibrium with B and B is in equilibrium with C, then guess what? A and C are also in equilibrium. Now, we'll never touch that law again, but it's just kind of fascinating. The first law says that the energy of the universe is constant. Now, you may have heard that as you can neither create nor destroy energy. You need to push it around. So you have to be exothermic or endothermic. You have to do work. You have to heat. But you can't just say, whoa, found some energy. No, you did not. That energy had to come from someplace. Okay, there's an equation that goes with that. Any change in internal energy has to be equal to change in heat, this Q. Q's weird. You would never have chosen a Q to represent heat, but chemists did. And so the internal energy is equal to your change in your change in heat plus your work done. Okay, so any heat that you add or lose and any physical work that is done adds up to be your internal energy. It's another way of restating this, saying you can't just make energy. You have to push it in by work or heat. So that's going to lead us to another term, this thing called enthalpy. And for us in AP Chem, it's just heat. Heat and enthalpy are really the same thing in AP Chem because the difference is that enthalpy is heat when there's no physical work done by the system. Okay, so we will avoid systems in which gases have to push things out of the way. We will avoid systems where liquids get hot and have to do like stretching, pushing work. We are basically going to stay at room pressure all the time, and we're going to allow our chemicals to react in open beakers so that they can easily just change without having to do work on the system. And if we stay in that like simple system, enthalpy and heat are basically the same. If you go on to college, your college professor is going to tell me that I'm totally wrong and he is correct or she is correct. I am lying to you. But for AP Chem, enthalpy is heat flow. Got it? The big difference is that enthalpy is measured in joules per mole. Heat is just measured in joules. Okay, so the big thing is this enthalpy is not really an absolute concept. It's how much energy does each mole have? Okay, I'm going to leave you there. So do you know that energy must be pushed around from system to surrounding? You can't create it. And did you know that enthalpy is effectively just the flow of heat between system and surroundings? All right, good luck.